Hi everyone. Today I'm going to present this paper called Causal AF, which is Causal Autoregressive Flow for Safety Critical Driving Scenario Generation. So I am the presenter and I'm Reggie Liu. And Zhongwen Wu will be the critic and ask me questions at the end of the presentation. In this presentation, I will talk about the purpose of this new algorithm, how did they achieve it, what experiment did they do, and the conclusion. I'll first talk about the abstract of this paper. First of all, we should know the safety critical scenarios are effective ways to evaluate autonomous driving systems, but the data about the safety critical scenarios are difficult to collect. As a result, the diversity and efficiency of generated scenario are restricted by the rareness and structure of safety critical scenarios. So the author of this paper proposed a new flow-based generative framework called Causal Autoregressive Flow. This framework will encourage the generative model to uncover and follow the causal relationship among generative objects via normal causal masking operation that we will talk about later, instead of searching the sample only from observational data like previous existed method. Based on the experiment result at the experiment section of this paper, this framework significantly improved efficiency and could improve algorithm robustness when adding the generative model to the training dataset. In this section, I will talk about how the author of this paper came up with Causal AF and the pipeline of Causal AF. So as mentioned in the first paragraph, many autonomous vehicles nowadays succeed in normal scenarios but are unsure of their performance in safety critical scenarios such as a kid ran into the middle of the road suddenly. So previously we could use the deep generative models to estimate the uh, distribution of data sample with neural networks, but it is still challenging and insufficient because we have to avoid the scenarios that will never happen in real world. So as a result, the author of this paper proposed Causal AF to avoid this situation. As we could see in the pipeline chart, the causal graph represents the causal priorities between the generative object, and they propose COM and CVM, these two causal max, which will COM will modify the node order for node generation, and the CVM will remove irrelevant information for edge generation. And then we could facilitate the CG into the BG. So BG is a behavior graph that will represent the interaction between the object in scenarios. And as a result, the flowchart is very easy to understand. So the graphical representation of scenarios, which is BG, behavior graph, could describe the behaviors and interaction of static and dynamics object in the graph, as we talked about before. As we could see in the definition paragraph, GB it's a high-level planner based on VB and EB, and the self-loop II means it is irrelevant to other object, and IJ means it will have action on the J object. And at the end, the edge attribution represents the property of the action. Uh, in this paper, the author utilized the autoregressive flow model to generate a graph. First of all, the AF model sequentially generates dimension to generate nodes and edge of the graph step by step. And to generate nodes and edges, these variables are obtained from the F file in an autoregressive manner using the equation 4. Then the node and edge type are obtained by converting VB and part of EB from continuous value to one hot vector using equation 5. So the generation of one node depends on all previous generative nodes and edge. One node only has one edge pointing to the nodes that are generated before it. An example with three nodes is provided in Figure 2a to illustrate this regressive generation process. In this section, the purpose is to integrate causality into the autoregressive generative process of the behavior graph GB. In order to do so, they will use causal order mask (COM) and causal visible mask (CVM) to make the generative GB follow the causal information. As shown in the top right, it shows the definition for the structured causal models (SCM) and causal graph (CG). And the bottom right shows the generative process of a behavior graph and the causal graph and behavior graph using in the example of A and then the example of CVM when generating edge for C. It shows that one node will only depend on all the previous node and edge, as we talked about before. Let's talk about the causal order mask and causal visible mask. So for the causal order mask, they are used to ensure that the generation of each node follows a topological order in the directive acyclic graph. This means that a node is only generated after all its parent nodes have been generated. The mask is represented as a low triangular matrix M, where each entry Mij is equal to 1 if node I can depend on node J and 0 otherwise. In other words, the mask ensures that each node can only depend on previously generated node. And for the causal visible mask, on the other hand, are used to ensure that each edge in the graph is only generated once its source node has been generated. The mask is represented as a matrix MV, where each entry MVIJ is equal to 1 if node I can have an outgoing edge to node J and 0 otherwise. The mask ensures that each node can only have outgoing edge to previously generated node. So these two are pretty much the same, but one is about the node and one is about the edge. Let's move into the experiment section. First of all, the most important in the experiment is the scenario. So the scenarios will contain three objects. First one is traffic light, and then the pedestrian, and the second one is lane changing. After that, we need to have a simulator. So the author implement the above scenarios into a 2D simulator where all the agents have a radar sensor and are controlled by a simple vehicle dynamics. And the third part we need to have is baseline algorithm. So the authors tested 6 different algorithms as baseline, including 4 scenarios generation methods and 2 variants of causal AF to examine the contribution of COM and CVM on the final result. And as we could show in the right graph, we could see that the causal AF will have the best result. Also, other experiment results shows that the agent trained with generative scenario have better performance in safety-critical scenarios, which illustrates the importance of generating scenarios that are rare in the real world to the autonomous driving system. Also, as we could see in the figure in the right, you can see that training object of causal AF and 2 variant under 2 sampling temperature. And as we could see from the figure, the higher the sampling temperature is, the more diverse the generative scenarios are. Finally, let's give a conclusion of this paper. So this paper introduced a new method for generating safety-critical scenarios using a causal generative model. The model incorporates causality by using causal graph obtained from human prior to regularize the generation of behavior graphs, which will represent traffic scenarios. The regularization is achieved by modifying the generating order and graph connection with two causal masks COM and CVM. The goal is to efficiently create safety-critical scenarios that may be too rare to find in the real world. Also, the proposed method, uh, Casual AF, is equivalent on three environments with clear causality. The experiment result shows that Casual AF outperform all baseline algorithms in terms of efficiency and performance. Additionally, the paper demonstrates that training on the generative safety-critical scenarios improves the robustness of RL-based driving algorithms. Overall, this paper presents a promising approach to generating safety-critical scenarios that incorporate causality in a normal way, and the results suggest that the proposed method could be useful for training and testing autonomous driving algorithms in challenging and rare scenarios. And that's all. Thanks.